Group 3 element. Group 3 is a group of elements in the periodic table. This group, like other D-block groups, should contain 4 elements, but it is not agreed what elements belong in the group. Scandium and Yttrium are always included, but the other 2 spaces are usually occupied by Lanthanum and Actinium, or by Lutetium and Lawrencium. Less frequently, it is considered the group should be expanded to 32 elements or contracted to contain only Scandium and Yttrium. When the group is understood to contain all of the lanthanides, its trivial name is the rare earth metals. 3 Group 3 elements occur naturally: Scandium, Yttrium, and either Lanthanum or Lutetium. Lanthanum continues the trend started by 2 lighter members in general chemical behavior, while Lutetium behaves more similarly to Yttrium. While the choice of Lutetium would be in accordance with the trend for period 6 transition metals to behave more similarly to their upper periodic table neighbors, the choice of Lanthanum is in accordance with the trends in the S block, which the group 3 elements are chemically more similar to. They all are silvery white metals under standard conditions. The 4th element, either actinium or Lawrencium, has only radioactive isotopes. Actinium, which occurs only in trace amounts, continues the trend in chemical behavior for metals that form tripositive ions with a noble gas configuration. Synthetic Lawrencium is calculated and partially shown to be more similar to Lutetium and Yttrium. So far, no experiments have been conducted to synthesize any element that could be the next group 3 element. Unbionium, which could be considered a group 3 element if preceded by Lanthanum and Actinium, might be synthesized in the near future, it being only 3 spaces away from the current heaviest element known, Occurrence. In 1787, Swedish part-time chemist Carl Axel Arrhenius found a heavy black rock near the Swedish village of Ytterby, Sweden. Thinking that it was an unknown mineral containing the newly discovered element tungsten, he named it ytterbite. Finnish scientist Johan Gadolin identified a new oxide or earth in Arrhenius' sample in 1789, and published his completed analysis in 1794. In 1797, the new oxide was named yttria. In the decades after, French scientist Antoine Lavoisier developed the first modern definition of chemical elements, it was believed that earths could be reduced to their elements, meaning that the discovery of a new earth was equivalent to the discovery of the element within, which in this case would have been yttrium. Until the early 1920s, the chemical symbol Yt was used for the element, after which Y came into common use. Yttrium metal was first isolated in 1828 when Friedrich Wöhler heated anhydrous yttrium chloride with potassium to form metallic yttrium and potassium chloride. In 1869, Russian chemist Dmitry Mendeleev published his periodic table, which had empty spaces for elements directly above and under yttrium. Mendeleev made several predictions on the upper neighbor of yttrium, which he called EKA boron. Swedish chemist Lars Fredrik Nilsson and his team discovered the missing element in the minerals euxenite and gadolinite and prepared 2 grams of scandium oxide of high purity. He named it Scandium, from the Latin Scandia meaning Scandinavia. Chemical experiments on the element proved that Mendeleev's suggestions were correct. Along with discovery and characterization of gallium and germanium, this proved the correctness of the whole periodic table and periodic law. Nilsson was apparently unaware of Mendeleev's prediction, but Peter Cleve recognized the correspondence and notified Mendeleev. Metallic scandium was produced for the first time in 1937 by electrolysis of a eutectic mixture, at 700–800 degrees C, of potassium, lithium, and scandium chlorides. In 1751, the Swedish mineralogist Axel Fredrik Cronstedt discovered a heavy mineral from the mine at Bastnäs, later named cerite. 30 years later, the 15-year-old Wilhelm Heisinger, from the family owning the mine, sent a sample of it to Carl Scheele, who did not find any new elements within. In 1803, after Heisinger had become an iron master, he returned to the mineral with Jöns Jacob Berzelius and isolated a new oxide which they named Syria after the dwarf planet Ceres, which had been discovered 2 years earlier. Syria was simultaneously independently isolated in Germany by Martin Heinrich Klaproth. Between 1839 and 1843, Syria was shown to be a mixture of oxides by the Swedish surgeon and chemist Carl Gustav Mosander, who lived in the same house as Berzelius. He separated out two other oxides which he named Lanthanum and Yttrium. He partially decomposed a sample of cerium nitrate by roasting it in air and then treating the resulting oxide with dilute nitric acid. Since lanthanum's properties differed only slightly from those of cerium, and occurred along with it in its salts, he named it from the ancient Greek lambda alpha nu theta nu epsilon iota nu. Relatively pure lanthanum metal was first isolated in 1923. Lutetium was independently discovered in 1907 by French scientist Georges Urbain, Austrian mineralogist Baron Karl Auer von Welsbach, and American chemist Charles James as an impurity in the mineral ytterbia, which was thought by most chemists to consist entirely of ytterbium. Welsbach proposed the names Cassiopeium for element 71 and Aldebaranium for the new name of ytterbium, but these naming proposals were rejected, although many German scientists in the 1950s called the element 71 Cassiopeium. Urbain chose the names neoytterbium for ytterbium and lutetium for the new element. The dispute on the priority of the discovery is documented in two articles in which Urbain and von Welsbach accuse each other of publishing results influenced by the published research of the other. The Commission on Atomic Mass, which was responsible for the attribution of the names for the new elements, settled the dispute in 1909 by granting priority to Urbain and adopting his names as official ones. An obvious problem with this decision was that Urbain was one of the four members of the Commission. The separation of lutetium from ytterbium was first described by Urbain and the naming honor therefore went to him, but neoytterbium was eventually reverted to ytterbium, and in 1949, the spelling of element 71 was changed to lutetium. Ironically, Charles James, who had modestly stayed out of the argument as to priority, worked on a much larger scale than the others, and undoubtedly possessed the largest supply of lutetium at the time. André-Louis de Bierne, a French chemist, announced the discovery of actinium in 1899. He separated it from pitchblende residues left by Marie and Pierre Curie after they had extracted radium. In 1899, de Bierne described the substance as similar to titanium and as similar to thorium. Friedrich Oskar Giesel independently discovered actinium in 1902 as a substance being similar to lanthanum and called it ammonium in 1904. After a comparison of the substance's half-lives determined by de Bierne, Harriet Brooks in 1904, and Otto Hahn and Otto Sacker in 1905, de Bierne's chosen name for the new element was retained because it had seniority, despite the contradicting chemical properties he claimed for the element at different times. Lawrencium was first synthesized by Albert Ghiorso and his team on February 14, 1961, at the Lawrence Radiation Laboratory at the University of California in Berkeley, California, United States. The first atoms of Lawrencium were produced by bombarding a 3 mg target consisting of 3 isotopes of the element californium with boron-10 and boron-11 nuclei from the heavy ion linear accelerator. The nuclide 257,103 was originally reported, but then this was reassigned to 258,103. The team at the University of California suggested the name Lawrencium and the symbol LW for the new element, but LW was not adopted, and LR was officially accepted instead. Nuclear physics researchers in Dubna, Soviet Union, reported in 1967 that they were not able to confirm American scientists' data on 257,103. 2 years earlier, the Dubna team reported 256,103. In 1992, the IUPAC Transfermium Working Group officially recognized element 103, confirmed its naming as Lawrencium, with symbol LR, and named the nuclear physics teams at Dubna and Berkeley as the co-discoverers of Lawrencium. So far, no experiments were conducted to synthesize any element that could be the next Group 3 element. If lutetium and Lawrencium are considered to be Group 3 elements, then the next element in the group should be element 153, unpentrium. However, after element 120, filling electronic configurations stops obeying Aufbau principle. According to the principle, unpentrium should have an electronic configuration of 8s25G186F147D1 and filling the 5G subshell should be stopped at element 138. However, the 7d orbitals are calculated to start being filled on element 137, while the 5G subshell closes only at element 144, after filling of 7d subshell begins. Therefore, it is hard to calculate which element should be the next group 3 element. Calculations suggest that unpent pentium could also be the next group 3 element. If lanthanum and actinium are considered group 3 elements, then element 121, unbionium, should be the fifth group 3 element. The element is calculated to have electronic configuration of 8s28p1/21, which is not associated with transition metals, without having a partially filled d subshell. No experiments have been performed to create unpentrium, unbionium, or any element that could be considered the next group 3 element. However, unbionium is the element with the lowest atomic number that has not been tried to be created and thus has chances to be, while unpentrium, unpent pentium or any other element considered if preceded by Lawrencium is very unlikely to be created due to drip instabilities that imply that the periodic table ends soon after the island of stability at unbihexium. Like other groups, the members of this family show patterns in their electron configurations, especially the outermost shells, resulting in trends in chemical behavior. However, Lawrencium is an exception, since its last electron is transferred to the 7p1/2 subshell due to relativistic effects. Most of the chemistry has been observed only for the first 3 members of the group. Chemical properties of both actinium and especially Lawrencium are not well characterized. The remaining elements of the group are reactive metals with high melting points. They are usually oxidized to the +3 oxidation state, even though scandium, yttrium, and lanthanum can form lower oxidation states. The reactivity of the elements, especially yttrium, is not always obvious due to the formation of a stable oxide layer, which prevents further reactions. Scandium oxide, yttrium oxide, lanthanum oxide, and lutetium oxide are white high-temperature melting solids. Yttrium oxide and lutetium oxide exhibit weak basic character, but scandium oxide is amphoteric. Lanthanum oxide is strongly basic. Elements that show tripositive ions with electronic configuration of a noble gas show a clear trend in their physical properties, such as hardness. At the same time, if group 3 is continued with lutetium and Lawrencium, several trends are broken. For example, scandium and yttrium are both soft metals. Lanthanum is soft as well. All these elements have their outermost electrons quite far from the nucleus compared to the nuclei charges. Due to the lanthanide contraction, lutetium, the last in the lanthanide series, has a significantly smaller atomic radius and a higher nucleus charge, thus making the extraction of the electrons from the atom to form metallic bonding more difficult, and thus making the metal harder. However, lutetium suits the previous elements better in several other properties, such as melting and boiling points. Very little is known about Lawrencium, and none of its physical properties have been confirmed. It is disputed whether lanthanum and actinium should be included in group 3, rather than lutetium and Lawrencium. Other d-block groups are composed of 4 transition metals, and group 3 is sometimes considered to follow suit. Scandium and yttrium are always classified as group 3 elements, but it is controversial which elements should follow them in group 3, lanthanum and actinium or lutetium and Lawrencium. Seri has proposed a resolution to this debate on the basis of moving to a 32-column table and consideration of which option results in a continuous sequence of atomic number increase. He thereby finds that group 3 should consist of SC, Y, Lu, Lr. The current IUPAC definition of the term lanthanoid includes 15 elements including both lanthanum and lutetium, and that of transition element applies to lanthanum and actinium, as well as lutetium but not Lawrencium, since it does not correctly follow the Aufbau principle. Normally, the 103rd electron would enter the d subshell, but quantum mechanical research has found that the configuration is actually 7s25f147p1 due to relativistic effects. IUPAC thus has not recommended a specific format for the inline F-block periodic table, leaving the dispute open. Group 3 of the periodic table as consisting either of the elements SC, Y, Lu, and Lr, or the elements SC, Y, La, and AC. The La and AC variant remains the most common in the literature, despite some calls for a change to the Lu and Lr variant. In terms of chemical behavior, and trends going down Group 3 for properties such as melting point, electronegativity, and ionic radius, Scandium, Yttrium, Lanthanum and Actinium are similar to their Group 1-2 counterparts. In this variant, the number of F electrons in the most common ions of the F block elements consistently matches their position in the F block. For example, the F electron counts for the trivalent ions of the first 3 F block elements are Ce1, Pr2, and Nd3. Scandium, Yttrium, Lanthanum, and Lutetium tend to occur together with the other lanthanides in the Earth's crust, and are often harder to extract from their ores. The abundance of elements in Earth's crust for Group 3 is quite low. All the elements in the group are uncommon, the most abundant being Yttrium with abundance of approximately 30 parts per million. The abundance of Scandium is 16 ppm, while that of Lutetium is about 0.5 ppm. The abundance of Lanthanum is greater, being about 35 ppm. For comparison, the abundance of copper is 50 ppm, that of chromium is 160 ppm, and that of molybdenum is 1.5 ppm. Scandium is distributed sparsely and occurs in trace amounts in many minerals. Rare minerals from Scandinavia and Madagascar such as gadoliniite, euxenite, and thortveitite are the only known concentrated sources of this element, the latter containing up to 45% of scandium in the form of scandium oxide. Yttrium has the same trend in occurrence places. It is found in lunar rock samples collected during the American Apollo project in a relatively high content as well. The principal commercially viable ore of lutetium is the rare earth phosphate mineral monazite, PO4, which contains 0.003% of the element. The main mining areas are China, United States, Brazil, India, Sri Lanka, and Australia. Pure lutetium metal is one of the rarest and most expensive of the rare earth metals, with the price about $10,000 USD/kg, or about 1/4 that of gold. Lanthanum is much more common, being the second most abundant rare earth, and in addition to monazite can also be extracted economically from bastnasite. The most available element in Group 3 is yttrium, with annual production of 8,900 tons in 2010. Yttrium is mostly produced as oxide, by a single country, China. Lutetium and scandium are also mostly obtained as oxides, and their annual production by 2001 was about 10 and 2 tons, respectively. Group 3 elements are mined only as a byproduct from the extraction of other elements. The metallic elements are extremely rare. The production of metallic yttrium is about a few tons, and that of scandium is in the order of 10 kg per year. Production of lutetium is not calculated, but it is certainly small. The elements, after purification from other rare earth metals, are isolated as oxides. The oxides are converted to fluorides during reactions with hydrofluoric acid. The resulting fluorides are reduced with alkaline earth metals or alloys of the metals. Metallic calcium is used most frequently. For example, Group 3 elements are generally hard metals with low aqueous solubility, and have low availability to the biosphere. No Group 3 element has any documented biological role in living organisms. The radioactivity of the actinides generally makes them highly toxic to living cells, causing radiation poisoning. Scandium has no biological role, but it is found in living organisms. Once reached a human, scandium concentrates in the liver and is a threat to it. Some its compounds are possibly carcinogenic, even though in general scandium is not toxic. Scandium is known to have reached the food chain, but in trace amounts only. A typical human takes in less than 0.1 micrograms per day. Once released into the environment, scandium gradually accumulates in soils, which leads to increased concentrations in soil particles, animals, and humans. Scandium is mostly dangerous in the working environment, due to the fact that damps and gases can be inhaled with air. This can cause lung embolisms, especially during long-term exposure. The element is known to damage cell membranes of water animals, causing several negative influences on reproduction and on the functions of the nervous system. Yttrium has no known biological role, though it is found in most, if not all, organisms and tends to concentrate in the liver, kidney, spleen, lungs, and bones of humans. There is normally as little as 0.5 mg found within the entire human body. Human breast milk contains 4 ppm. Yttrium can be found in edible plants in concentrations between 20 ppm and 100 ppm, with cabbage having the largest amount. With up to 700 ppm, the seeds of woody plants have the highest known concentrations. Lutetium has no biological role as well, but it is found even in the highest known organism, the humans, concentrating in bones, and to a lesser extent in the liver and kidneys. Lutetium salts are known to cause metabolism and they occur together with other lanthanide salts in nature. The element is the least abundant in the human body of all lanthanides. Human diets have not been monitored for lutetium content, so it is not known how much the average human takes in, but estimations show the amount is only about several micrograms per year, all coming from tiny amounts taken by plants. Soluble lutetium salts are mildly toxic, but insoluble ones are not. Lanthanum is not essential for humans and has a low to moderate level of toxicity. However, it is essential for the methanotrophic bacterium Methylacidiphyllum fumariolicum solvi, although the general similarity of the rare earths means that it may be substituted by some of the other early lanthanides with no ill effects. The high radioactivity of Lawrencium would make it highly toxic to living cells, causing radiation poisoning. The same is true for actinium. The Scandium subgroup comprises Scandium, Yttrium, Lanthanum, and Actinium. In addition, the element of the cerium and thorium families are also included in the subgroup. The main characteristics of Scandium and its analogous are summarized below. Atomic number 213957. Atomic WT. Valency electron. Scandium and its analogous are the first d elements of Thayer period, i.e. they are the first whose d subshell of the penultimate shell being to be filled. The presence of just one electron in the d state accounts for the stability oxidation state of 3 in Scandium and its analogous. The stable CO ordination number increases in the transition from Scandium to Yttrium and